According to the 2011 National Electrical Code, it is permitted to land two neutral conductors under one terminal, provided that the terminal is rated and acceptable for that purpose. This is covered in National Electrical Code section 300.13. It's crucial to verify that the terminals are indeed rated for multiple conductors. Terminals designed for multiple conductors will typically be marked or labeled to indicate the number and size of conductors they can accommodate. This information is essential for ensuring a safe and code-compliant installation. The neutral conductors must be landed correctly, which involves ensuring proper torque. Torque is the rotational force applied when tightening a screw or bolt. Electrical connections require specific torque values to ensure secure and reliable connection. Under-torquing can lead to loose connections, causing increased resistance, heat generation, and potentially electrical fires. Over-torquing can damage the terminal or conductor, also leading to connection failures. Using a calibrated torque screwdriver or wrench is essential for achieving the correct torque. The manufacturer's instructions for the specific terminal and conductor size will specify the appropriate torque value. This is a critical step in preventing electrical hazards and ensuring long-term reliability. Therefore, it is not a code violation in this instance. However, it is important to note that this permission is only valid if the neutral conductors are of the same size. Mixing different sized neutral conductors under one terminal is not permitted. If the neutral conductors are of different sizes, they must be landed on separate terminals. This requirement is based on the principle of current distribution. When conductors of different sizes are connected in parallel, they do not share current proportionally to their ampacity. The smaller conductor will carry a higher current density, potentially exceeding its ampacity and leading to overheating and failure. This is why the National Electrical Code mandates separate terminals for different sized neutral conductors. Also note that the feeder neutral is to be isolated and insulated from equipment grounding conductors as per National Electrical Code section 250.24d. The feeder neutral, also known as the grounded conductor, carries the imbalanced current from the load back to the source. It's typically a white or grey insulated wire. Equipment grounding conductors, on the other hand, provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. These are typically bare or green insulated wires. National Electrical Code section 250.24d mandates that the feeder neutral be isolated and insulated from the equipment grounding conductors at the service entrance. This separation is critical for preventing objectionable current flow on the equipment grounding system. Objectionable current flow can create a number of problems, including nuisance tripping of ground fault circuit, interrupters, voltage drops, and electromagnetic interference. By isolating the feeder neutral, the code minimizes the possibility of current flowing through unintended paths. In summary, when dealing with multiple neutral conductors under a single terminal, several key considerations come into play. Firstly, verify the terminal rating. Always ensure that the terminal is specifically designed and listed for accommodating multiple conductors. This information can be found in the terminal itself, the packaging, or the manufacturer's specifications. Do not assume that a terminal can handle multiple conductors without proper verification. Secondly, conductor size uniformity is paramount. Only neutral conductors of the same size are permitted under a single terminal. Mixing conductor sizes can lead to unequal current distribution and potential overheating. If conductor sizes differ, each conductor must have its own dedicated terminal. Thirdly, proper installation techniques are crucial. Ensure that the conductors are properly stripped, inserted into the terminal, and tightened to the manufacturer's specified torque. Loose connections can cause arcing, overheating, and potentially electrical fires. Finally, adhere to National Electrical Code section 250.24d regarding feeder neutral isolation. Maintain the separation between the feeder neutral and the equipment grounding conductors to prevent objectionable current flow. By following these guidelines, you can ensure a safe and code-compliant electrical installation. To further elaborate on the concept of terminal ratings, it's essential to understand the different types of terminals available and their intended applications. One common type is the pressure connector, which uses a screw or bolt to clamp the conductor against a conductive surface. These connectors are typically rated for a specific range of conductor sizes and may or may not be listed for multiple conductors. Another type is the insulation displacement connector, or IDC, which pierces the insulation of the conductor to make contact with the wire. These connectors are often used in low voltage applications and may not be suitable for higher current circuits. A third type is the set screw connector, which uses a set screw to secure the conductor in place. These connectors are commonly used for grounding and bonding applications. When selecting a terminal, it's important to consider the ampacity of the circuit, the conductor size, the environmental conditions, and any applicable codes or standards. Always choose a terminal that is properly listed and rated for the intended application. The importance of maintaining separation between the feed-in neutral and the equipment grounding conductors cannot be overstated. In a properly wired electrical system, the neutral conductor carries the unbalanced current from the load back to the source, while the equipment grounding conductor provides a path for fault current to return to the source. These two conductors should only be bonded together at the service entrance or the source of a separately derived system, such as a generator or transformer. Bonding the neutral and ground at multiple locations can create parallel paths for current flow, leading to objectionable current in the equipment grounding system. This objectionable current can cause a variety of problems, including nuisance tripping of ground fault circuit interrupters, voltage drops, and electromagnetic interference. In some cases, they can even create a shock hazard. To prevent objectionable current flow, it's crucial to follow the National Electrical Code requirements for neutral and ground separation. This includes isolating the neutral conductor from the equipment grounding conductors throughout the distribution system and ensuring that all equipment is properly grounded. When dealing with older electrical systems, it's not uncommon to find instances where the neutral and ground conductors are improperly bonded together. This was a common practice in the past, but it is no longer permitted by the National Electrical Code. If you encounter this situation, it's important to correct the wiring to bring it into compliance with current code requirements. This typically involves separating the neutral and ground conductors at all locations except for the service entrance or the source of a separately derived system. It may also involve installing additional grounding electrodes to ensure that the equipment grounding system is properly grounded. Correcting improperly bonded neutral and ground conductors can significantly improve the safety and reliability of an electrical system. Furthermore, understanding the concept of multi-wire branch circuits is relevant. A multi-wire branch circuit consists of two or more ungrounded conductors that have a voltage between them, and a neutral conductor that is common to all of the ungrounded conductors. The neutral conductor carries only the unbalanced load. Multi-wire branch circuits can save conductors and conduit, but they must be properly wired to avoid overloading the neutral conductor. The National Electrical Code requires that the neutral conductor in a multi-wire branch circuit be sized to carry the maximum unbalanced load. It also requires that the ungrounded conductors be connected to different phases to minimize the current on the neutral conductor. In cases where the ungrounded conductors are connected to the same phase, the neutral conductor must be sized to carry the entire load. Multi-wire branch circuits can be a cost-effective way to wire a building, but they must be carefully designed and installed to ensure safety and compliance with the National Electrical Code. When working with electrical systems, it's always important to follow safe work practices. Firstly, always de-energize the circuit before working on it. Use a voltage tester to verify that the circuit is de-energized. Secondly, wear appropriate personal protective equipment, including safety glasses, gloves, and insulated tools. Thirdly, never work alone. Have someone nearby who can assist you in case of an emergency. Fourthly, be aware of your surroundings. Look for potential hazards, such as exposed wires, water, and sharp objects. Fifthly, follow all applicable codes and standards. The National Electrical Code is the primary standard for electrical safety in the United States. By following these safe work practices, you can minimize the risk of electrical shock and other injuries. In addition to the National Electrical Code, there may be other applicable codes and standards that you need to follow. For example, the National Fire Protection Association, or NFPA, publishes a number of standards related to electrical safety, including NFPA 70, Standard for Electrical Safety in the Workplace. This standard provides guidance on how to protect workers from electrical hazards. The Occupational Safety and Health Administration, or OSHA, also has regulations related to electrical safety. These regulations are designed to protect workers from electrical hazards in the workplace. It's important to be aware of all applicable codes and standards and to follow them carefully. To further illustrate the application of National Electrical Code Section 250.24d, consider a scenario involving a new service installation for a commercial building. The service consists of 480 volts, 3-phase, and 4-wire system. The neutral conductor is grounded at the service entrance as required by the National Electrical Code. The equipment grounding conductors are connected to a grounding electrode system which consists of a ground rod and a metal water pipe. The neutral conductor is isolated from the equipment grounding conductors throughout the distribution system. This means that the neutral conductor is not bonded to the equipment grounding conductors at any point other than the service entrance. All equipment is properly grounded, with the equipment grounding conductors connected to the grounding electrode system. This installation complies with National Electrical Code Section 250.24d and ensures that objectionable current will not flow on the equipment grounding system. Another important aspect of electrical safety is proper overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload occurs when a circuit is carrying more current than it is designed to handle. A short circuit occurs when there is a direct connection between two conductors that have a voltage difference between them. Both overloads and short circuits can cause excessive heat, which can lead to fires. Overcurrent protection devices are designed to trip or blow when the current exceeds a certain level, interrupting the flow of electricity and preventing damage to the circuit. It's important to select the correct overcurrent protection device for each circuit. The size of the overcurrent protection device should be based on the ampacity of the conductors in the circuit. The National Electrical Code provides tables that specify the ampacity of different types of conductors. It's also important to ensure that the overcurrent protection device is properly installed and maintained. Circuit breakers should be tested periodically to ensure that they are functioning properly. Fuses should be replaced with the correct size and type of fuse. Proper overcurrent protection is essential for preventing electrical fires and ensuring the safety of electrical systems. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs are designed to protect people from electrical shock. They work by monitoring the current flowing through a circuit and detecting any imbalance between the outgoing and return current. If there is an imbalance of 5 mA or more, the GFCI will trip, interrupting the flow of electricity. GFCIs are typically installed in areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. The National Electrical Code requires that GFCIs be installed in certain locations. GFCIs are very effective at preventing electrical shock, but they are not foolproof. It's still important to follow safe work practices when working with electricity. Arc fault circuit interrupters, or RFCIs, are another type of safety device that is designed to protect against electrical fires. RFCIs work by detecting arc faults, which are small electrical arcs that can occur in damaged or deteriorated wiring. These arcs can generate a lot of heat, which can ignite nearby combustible materials and cause a fire. RFCIs are designed to trip when they detect an arc fault, interrupting the flow of electricity and preventing a fire. The National Electrical Code requires that RFCIs be installed in certain locations, such as bedrooms. RFCIs are a relatively new technology, but they have been shown to be very effective at preventing electrical fires. In conclusion, understanding and adhering to the National Electrical Code, especially sections 300.13 and 250.24d, is paramount for ensuring safe and compliant electrical installations. This includes proper terminal selection, conductor sizing, neutral and ground separation, and the use of appropriate overcurrent protection and safety devices. Always prioritize safety and consult with a qualified electrician if you have any questions or concerns. Remember to verify terminal ratings, maintain conductor size uniformity, employ proper installation techniques, and adhere to feeder neutral isolation guidelines.